Imagine this is happened to you lah. Means like Allah already tested you with sickness. Then suddenly, I don't know how this is the rule lah. Okay. Again, so share the screen. Screen 2. Okay. So, then you mixed with VCT. Okay, means you modulate, right? You bring it to higher frequency. Then it will produce this VASK. Okay, amplitude shifting. So the equivalent, this one can be obtained by using an on and off switch. It's easy, but it is having disadvantage like shown in the video just now. Okay, you suddenly have one, totally have volts, suddenly you have 0 volts. Okay, of course it's simple because just like open and off switch, but the problem is in the realization and also we have some performance disturb lah, okay, like spectral regrowth and so on. Okay. So this one is not always on and off, but one of the way to achieve is on and off. So and with the band pass, if you are using this, okay, then you using that. Okay, then receiver, okay, means at the receiver side. Okay, at the receiver side means detection. Okay, means we're going to retrieve back the information signal. So you can see this is VASK, the one they already modulated. Then you have diodes. What is the diode for? It's actually to allow the signal to only have DC value, to have only one polar, means positive or negative. Okay. Half wave rectifier. So I'm not sure how tricky the question will be. Means don't assume it's always like positive all the time, right? Depends. It's as if like the tip is said we just want one polarity. So it can be either all negative or all positive. Cannot be both. Okay. So here is a low pass filter. So why we are having this? Because we are trying to remove the carrier. Because carrier is having high frequency. And the information is lower frequency, right? That's why only low frequency will pass. And then we get the information signal which is our VM. Okay. So this one is we are using coherent detector. Okay. If you are using coherent detector, this one is envelope detector like AM circuits. Okay. This one is coherent detector. So you have to mix with the carrier. Okay. So if the carrier is using 10 to the power of 6 frequency, so you're going to have cos 10 to the power of 6 as well. Okay, here. Then mix together, then you will go to low pass filter. Okay, so just like in AM FM, you have signal to noise ratio. Here you also have signal to noise ratio, but because your information signal is digital, so we measured using bit error because it's digital. Okay, so bit error rate. Okay, bit error rate because our information is in terms of digital. Okay, so BER is measured based on the differences between the send and receive bits in period T naught. It's the same lah. Means the one that we receive over the one that we send. How many errors? Means we send later we learn. Okay, ada dalam we have later in the slide. Okay, so normally the BR will depends on other factor such the modulation technique and NREB. Okay, So this one is E bit. Okay. And this one is the noise. Okay. As shown in figure 5.19. So when I check the module, there is no 5.19. Funny, this one. So we don't have this. You can check your module. I don't think there is figure. No, there is figure 5.19, but it's not relevant to this one. Maybe they put wrong caption. Okay. So SNR is energy per bit. You see here, energy per bit means energy per bit lah. Okay. And this one is noise power spectrum density if single-sided. If double-sided, n is, I don't know this, and not, if double-sided is, if I know n not over 2. Okay. This one is, so you need to take consideration whether this one is single-sided or double-sided. Okay. If single-sided, it's just n not. If double-sided, if I'm not mistaken, n not over 2. Okay. You will see this later. Okay. So this one is for ASK. Okay, only for ASK. So probability of error. Okay, probability that we will see error bit. Okay, for example, so this is the one that we receive, the one that we send. Okay, the one that we send means 8 bit of data, and then the one that we receive. So how many error bit we have? 2 error bit. So this one is error bit, not probability of error. Error bit. Okay. So PE is equals to half. This one is error function. Okay. It's not error, it's error function. You will use the appendix. Oh, I don't bring the appendix. There is error function table in the. Can you open your own appendix? I don't have. I forget. Where is it? Suddenly bersih pula. Suddenly no paper. Means I left home. So, this one, okay. When you have solved this, it will have some value, right? For example, you solve this, maybe it will become 3. When you solve this error function, 3.62, for example, this one 3.62. So the answer will be 2.85 times 10 to the power 97. Okay. All of this will be like RFC in bracket 3.61. And what the matching answer is? 331 times 10 to the power of 97. Okay. All of this, you take the value first to get the x. Okay. I think I have x. Okay. So it will be like error. If you solve ERFC 3.6, is it? Then the rest will be, then you check the matching table, the matching value. Okay. This one is imagine you get 3.61 lah, just imagine. Ada kan? Okay. And normally this table is approximation. Let's say I ask you to find 3.43. Okay, 3.43. Do you have 3.43 inside? So that one take your decision, taking which one is the closest. So which one is nearest? 3.0 or 3.45? But you do kan? Normally they will not give this kind of maybe they will give one that is closer lah. Maybe 3. Normally they say 3.41. Mean close to 3.1. Something like that. So you need to make decision lah. Okay. So you mesh to the nearest value, not just not salah lah. Okay, middle value susah you nak decide. Okay, middle value is a bit difficult to decide lah. So they will you need to see which one is the closest one. Okay, so this one is EB is average. Okay, average energy per bit. So you cannot take the maximum energy or minimum energy. This one is average. Okay. And next one is the noise power spectrum density per band. Okay, density per band. So we go to the next one. Frequency shifting. Okay. So this one is FSK. So this is just like FM. Analogy to FM lah, but it's not FM lah, right? Record ke tak ni? Sekejap Wait lah. Lah, tak record ke? Record. Sorry. Wait lah, I'm confused. Oh, record Oh, I didn't see this. It doesn't appear in my screen. Okay. So FSK. So you can see there is two carrier. Two carrier. So this is your information signal. This is your carrier. So you have two carrier, right? That's why you have omega C1 and omega C2. Which one is higher frequency? This one, right? Okay. This one is lower frequency lah, because you can see the one that is more compressed is higher frequency. Then this one is the information signal 101. Okay. And the next one is actually the inversion. Do you see this? It's just like inversion. So this, if this one is this 0, if this is 0, this is 1. If this is 1, this is 0. Later you will see lah. Okay. So then you get corresponding frequency for the information signals. Okay. Then this is your ASK1. Okay. ASK1. Because to produce FSK is actually we obtain it from ASK. Understand? That's why we get to produce FSK, we need ASK. Then ASK, what is the normal one? One that is inverted. That's why you have inverted here. Can you see? Okay. So this one is ASK1. This one is ASK2. Okay. And this one is the information signal is inverted. Okay. Then in the end, it will produce your produce FSK. Okay, FSK. With the frequency carrier omega C1, of course, and omega C2. And the rest is just depends on how many harmonics that you have. If we ask for 3 harmonics, mean this one will be omega C2 plus 5 omega, 3 omega. If it's 3 harmonics. Okay. The same goes for WC1 here. If you ask for 3 harmonic, mean this one will be omega C2, omega C1 minus 3 omega. Okay, so the same. Nampak kaki je tu apa ni, Daniel? Hisham. Okay. Oh, Danny tidur. Danny sleeping. Okay. So this one is FSK generations. So maybe not so clear here, but it's clear in your slide. Hopefully lah. Kalau tak clear, you zoom. If not clear, you zoom. Okay. So if you see, like I told you, FSK is we get it from 2 ASK, which is one of the ASK is inverted. Okay. So that's why you have inverter here. Okay. So this one is your signals. Okay. This one is your signal, the information signal. And the other one is inverted signals. Okay. This one is this one. Okay. Inverted. So if this is 101, so this one is, if this is 101, so this one will be 0, 1, 0. Okay. Then you will have V1 and you have V2. Okay. And then after that, you're going to modulate with this different frequency. And this is different frequency. Doesn't mean F1 always be smaller than F2. Doesn't mean that this carrier should be smaller than this F2. Doesn't mean that F2 always higher lah. Okay, you understand my logic, right? But it is a different frequency. Okay, different frequency. And of course, both F1 and F2 must be higher than the information signal because they are the carrier. Okay, and after that, you sum them together. So when you sum, this one I think is plus. Both of them is plus. So you can have plus minus, but this one is plus plus. Okay, and then you combine, you're going to have this AFFSK signals. Okay. So mathematically for analysis, VFK is actually V1 dot VC1 plus V2 dot VC2. This one logic, right? Because this one is coming from the positive here, coming from this one. Okay? And the rest is just multiplications of what you have lah. Okay. So where V1 is VM1T, and V2 is VM2T inversion. Okay, you understand, right? You know why this is 1 minus? Because this one is inversion of this one. Okay. V2 is actually inversion of V1, right? That's why we have 1 minus VM1T. If you study mathematics, this one is complementary. Means 1 minus the set. We'll get the complement. Okay. So this one is inverter lah. Okay, due to the inverter. So taking Fourier series, so this one is actually from your Sinai system. So VM1T, the rectangular, you get this. Okay, you get this. So now you expert already. Fourier series. Okay. So and VM2 is the complementary. Okay, complementary. So it's just 1 minus. Okay. So that's why we have just minus. Okay. So so 1 minus the entire of VM1T. Okay. So 1 minus half, you get half. And minus VM1T. So this one is just minus. Okay, understand? And we have VC, which we already know, the carrier, which is much higher than omega m. So therefore, VFSK is just a multiplication of VC1, VM1 times VC2, V2 empty. I think this one is quite straightforward. The problem is the question. Okay. I don't know question we ask what. Okay. It's just pretty straightforward, but hopefully that you remember the general lah. Since you know to produce FSK, you need 2 ASK, but one of the SK is inverted from the other ones, and this one ASK1 will be modulated with different carrier than the ASK2. Doesn't mean F2 must be higher than F1, but both F1 and F2 must higher than FM. Okay, that is the concept lah. Then you mix together to produce FSK. Question can be anything, but if you understand, should be okay lah. Okay. So bandwidth for FSK signal is up to third harmonics are considered. So if we consider up to third harmonics, means bandwidth equals to 6 FM. Okay. Plus 2 deviations. Okay. This one is deviations. So FC1, FC2 minus FC1 over 2. Okay. So for basic requirements, okay, basic means this one, what does it mean by basic? Means the most lowest standard. Like basic lah. Cannot be more worse than this. This is the lowest one that we can tolerate. So if the question asks you, what is the minimum criteria? What is the minimum that we still able to tolerate? So this FB plus 2 delta F lah. Means we're not considering all the harmonics, but only the FB. Okay. This one, only this, if for basic requirement. Okay. So this one is modulated FSK signals. Okay. Sorry, this is Malay. This one is modulated FSK signal. This one is mana nak terjemah English ni? This one is bandwidth. Okay, bandwidth, data bandwidth. So this one is for the bandwidth of why they use FSK. Okay, this one is the bandwidth of FSK. So this one is the bandwidth lah. Okay. So I give you 5 minutes. So now we finish until this. We continue the rest after. Okay, because I want to go to pass test 2. Okay, so we continue at 3:15. You can go toilet, whatever. Okay, I stop recording. So we continue at 3:10, at 3:15. Stop recording. Stop.